All right, so we're going to be doing the linear momentum, impulse, NMSI, free response key. Good news, kids. Got a little stylus now, so you're going to be able to read my writing. So let's go get into it. It's only one problem. Yeah, I think it's, one problem, so I'll read it. A group of students has two carts, A and B, with wheels that turn with no friction. The cart can travel along a straight horizontal track. Cart A has a known mass MA. The students are asked to use one-dimensional collision between the carts to determine the mass of cart B. Before the collision, cart A travels to the right, and cart B is initially at rest, as shown above. After the collision, the carts stick together. All right, so let's draw what we got here. So we got A is originally moving, B is at rest. Afterwards, they collide, stick together, and then move. All right, so there's our picture. Describe an experimental procedure to determine the velocity of the carts before and after collision. Include all the additional equipment you would need. You may need to include a labeled diagram of your setup to help in your description. Indicate what measurements you would take and how to take them. Include enough detail so another student can carry out your procedure. All right, so I'll give two ways to do it. I'll give, so the first way is this. So what's important is there's no outside forces acting on it. So once cart A is moving with a velocity, it's going to remain at that velocity. It's constant velocity. Then it's going to collide with cart B. It's going to collide, link together. Obviously, the velocity of the two carts after, all right, this velocity here after is going to be smaller than the velocity initial of cart A because they're combined masses. Okay, and remember, momentum is conserved. So I can say momentum before equals momentum after. All right. So what that means is once they hit, so the velocity initial the entire time it's before. Anytime here, it's going to be going the same velocity. Anytime after the collision, it's going to go the same velocity. All right, afterwards. So that's what it's saying. So we can use that information to come up with an experiment. So a basic way, so we could say procedure. We could put tape, so we could put like little pieces of tape right here. So I'll draw on the diagram here. Before, so at some point before and some point after. Some point before it collides and some point after, right? Well, and we can measure that distance d. So we need a, obviously a, meter stickers or whatever. Then same thing. We're gonna put some pieces of tape afterwards, sometime after it's collided, and sometime down here. So that's another distance d. So we got tape. Now all we need to do is you need some stopwatches. So what the key is the cart A has to already be moving with that velocity when it passes through the tape, because it's going to move, once it's moving, it's going to move at a constant speed in between. Likewise, it has to be after both carts start moving, because once they start moving, they're going to move at a constant speed, so you get some distance d here. All right? So what you do is you get time, you just use a definition here. So if you're trying to find velocity, you use, in our case, d divided by t. This, you get the same thing here, velocity equals d. And there you got your velocities. Is that all you needed? Yeah, so all you need to do to get your velocities. So procedure 2. This will just change up the equipment used. So instead of using meter stick or what's it called, stopwatch, what you can do is use one of those motion sensor. To get the velocity before. You set up a motion sensor on this side. The velocity after, and then you can just get the readings from the motion sensor, because what it should read is a constant velocity, right? This one should read it should be at 0 and then a constant velocity, right? So there's your velocity, whatever, because we said there's no friction, okay? So kind of the same thing, just using different equipment, all right? Let's clear this. And let's go to B. I'm not stamped. B. There will be sources of air in the experiment taken. There will be sources of air in the experiment taken in the experiment. In the measurement, I can't read. In the measurement taken in the experiment, both before and after the collision. For your experimental procedure, will the uncertainty in the calculated values of the mass car B be affected more by the air in the measurements taken before the collisions or those taken after the collision? Or will it equally affected by both sets of measurements? All right, so let's look at it first. So like I said here, yeah, this scenario going, this is A, it's moving, B is at rest, and then B, and they move down. And we said that velocity initial of A is going to be greater than velocity final of both A and B. It's going to be smaller, right? So the velocity is actually going to decrease here. So let's think about it this way. Let's say, you know, wherever the air is, maybe it's in our stopwatch, right? We're going to say that to compare it, the measurements taken, the source of air, the air in the measurement is going to be the same before and after, right? So if the air is the same before and after, okay, the air is going to be in what what the experiment's designed to get, which is velocity, right? So the air is going to be in those terms. So if we have the same amount of air, but this is a smaller velocity, when I compare the ratio, in other words, if I get a percent air and I have the same amount of air as here, I'm going to get a higher percent of air as compared to when I have the same amount of air in here, because it's a higher velocity that's giving you a lower percent of air. So an error in the second half is going to affect it more because it's going to give you a higher percent air. Okay, so that's going to affect the mass B more. Now, something else you could point out when you're doing this is you could say, okay, let's say that you know, it's not going to be equal, right? If the air is not going to be equal, right? Maybe it's, you know, we're just talking about our stopwatch, okay? So you could go that route, or you could go this route. You could say, all right, I think there's going to be more air in the initial part because it's moving faster. So think about it. If you're trying to time something, right, and you're trying to start it and stop it at a certain point, if something's moving faster, right, isn't it harder to get it exactly at that measured point and as it's moving slower, right? You can kind of see it moving. So what we're saying in the first part, the first answer I gave here was if the air is exactly the same, all right, then it's going to affect B more. B will affect the mass more. Now, if we're saying that the air is not going to be the same, we're just thinking about the experiment, and what we can say is, okay, it's harder to time, because that's what our first experiment was. It's harder to time something moving faster. There could be more air in that. If there's more air, then the percent air will go up, thus A, or the before collision will affect the mass more. So you see the difference. We're saying same in this part, different in the second part. All right? So they would accept either answer there, kind of, just had to kind of explain that. All right? So let's see what C says. All right. So it gives you a graph. It says a group of students took measurements for one collision. A graph of the students' data is shown below. Given mass A, so I got mass A is equal to 0.5 kilograms. Use the graph to calculate the mass of car B. All right. So let's go back to the picture. I drew it twice, so I hope I don't need to do it. So if I start with this equation, momentum before equals momentum after. I think about, remember when we're doing this, you ask yourself how many things were moving. Well, I had mass of A times velocity initial. Only one thing was moving. I'm only going to have one thing. So I set it equal to because the carts collide. Now think about afterwards, how many things are moving? Well, I got two carts moving, but they're moving together. So what I do here is I do MA plus MB velocity. All right. So this, if I know mass A, it's given to me. I'm going to find our experiment was designed to find velocity initial and velocity final. The only term left is the mass of cart B, which we want to find. So it says, I actually have to calculate it. Oh, let me see if I did it. Yeah. So what we have is a position versus time graph. So again, this goes back to a one-dimensional motion. If you have a position versus time graph, you should use the slope to find the velocity. So I got a versus time graph. What you need to do here is you need to draw a line of best fit. I'm not going to write all of this out, but what it should look like is something like this until about 1 second. And 1.2 seconds. And then it kind of flattens out, so your line of best fit should be somewhere like that. All right. So obviously the slope in the second half went down as compared to here. Okay, that's because of velocity decrease, like we said the whole time. We've been comparing the velocities. So what you need to do here is you need to calculate the slope of your line of best fit. I'm going to go off mine. As long as your answer is kind of close, they're going to accept it because it just shows off a line of best fit. There's a little bit of room for error. So let's find velocity before. I got for my slope, so I got slope equals delta y over delta x. My change in y I got to be 1.4 is the final y minus 0 because it went through the vertex. 0.9 minus 0, and I get somewhere around 1.55 meters per second. All right, so let's do velocity after. Slope, same equation. My numbers I used here, I think were 2.2 minus 1.7 and 2.1 minus 1.3 at the 2. I get somewhere around 0.0 meters per second. All right. Now again, if you're close, again, I drew my line of best fit, and I took the numbers from there as best I could and stuff like that. As long as what you need to show is you're looking for the slope. As long as they see you're looking for the slope and you do it right, as long as it's close, you're good to go. So then what I can do is plug in. I know the mass here is 0.5. Velocity initial is your 1.55 equals 0.5 plus mass B. Velocity 0.3. I get mass B equals, for me, 0.73, I think it is, 0.73. All right. So key is slope, and then this equation here, making that one wrong. All right, pretty straightforward. All right, the students are now asked to consider kinetic energy changes in an inelastic collision. Hopefully you remember what an inelastic collision is. Specifically, whether the initial values of one of the physical quantities affect the fraction of mechanical energy dissipated in the collision. How could you modify the experiment to investigate this question? Be sure to explicitly describe the calculations you would make, specifying all equations you would use, but not actually doing any algebra or arithmetic. All right, so what they're saying is you need to compare how much kinetic energy was lost, comparing it to if you change different things at the start. So in other words, if you look at kinetic energy equation, there's two different ways you can change it. You can change it by the mass, or you can change it by the velocity. So what we're going to be doing is the same experiment, so the same before and after. So what you want to do is you want to pick one of those and say, okay, I'm going to change the velocity a couple times, right? So I do it, I run the experiment, I get a velocity initial, I get a velocity final. I'm going to do the same thing. So then what you're going to do is you want to take a change in kinetic energy. You're going to compare that to the initial kinetic energy. So if this ratio, that's a ratio, you're going to be looking at. So if I increase, so just say for sake of it, I'm going to start with just the velocity, right? So if I increase the velocity, so I do it once with the start velocity, and I get this ratio. Now I'm going to increase the velocity, do the same thing. My kinetic energy final should also increase because I have more, more velocity. But what I'm looking at is how much energy is lost compared to the initial kinetic energy. So if that ratio stays the same, then changing the velocity doesn't affect that. Okay, you can do it multiple times, a couple times to see if you get the same ratio. Then what you could do is then look at the mass. If I start changing the mass of the car, I start with an empty cart. I do it. I look at the same same ratio here. I then add mass. If I add mass to it, it's going to change my kinetic energy. Again, now I'm keeping the velocity the same. I need to have the same velocity, so I'm isolating that variable. And I look at my kinetic energy final. I compare the same ratio, and I look. All right, if that ratio is different, then then that variable changes. It affects the loss or gain of kinetic energy differently. All right. I think that was it. All right.